This is Stanford Engineering's The Future of Everything, and I'm your host, Russ Altman. If you enjoy the Future of Everything podcast, please follow it on whatever app you're listening to right now. That will guarantee that you never miss an episode and you're totally clued in on the future of everything. Today, Kristen Davis will tell us that seaweed may be part of the solution to carbon dioxide excess in the atmosphere. Turns out the ocean might be able to absorb the CO2 with seaweed, and then we can store it in the long term at the bottom of the ocean. It's the future of seaweed. Before we get started, please remember to follow the show by pressing the follow button on the app that you're listening to and making sure that you never are surprised by the future of anything. You know, we've heard about greenhouse gases, especially carbon dioxide, CO2, as a major problem for global warming. And one of the things we're all trying to do is reduce our carbon emissions to try to help with that excess that is currently heating up the planet. But in addition to reducing our production, it would be good to also increase our consumption. Trees are one way that happens. Trees absorb CO2, and through the miracle, and I do mean miracle, of photosynthesis, they turn it into organic things like sugar. Well, and wood bark and leaves. Well, guess what? You can grow seaweed in the ocean, and it can do some similar things in terms of storing CO2 and turning it into organic matter. That organic matter could then be kept in the ocean. It can be harvested for us to eat, yummy, or many other things. Well, Kristen Davis is a professor of oceans at Stanford University and an expert on the biophysics of oceans, their interaction of the ocean with the coast, and she's increasingly looking at the interaction of the ocean with CO2. She's going to tell us that seaweed might be the answer or part of the answer to consuming more CO2 and ameliorating the problems with global warming and greenhouse gases. Kristen, you study global CO2 and its interaction, especially with the ocean. Before we get into some of the exciting ideas you have for ways to manage this, can you kind of explain what's the CO2 problem? Where did it come from? I know that's somewhat controversial. And how urgent is it right now?
Hi, Russ. Thanks for asking. I think we all understand that we have too much CO2, or sometimes they're called greenhouse gases, in our atmosphere. But what I think sometimes gets overlooked is, with the focus on the atmosphere, is that the oceans actually interact with the atmosphere in a really important way. The oceans historically have played a large role in taking up some of that CO2 and actually buffering or mitigating some of our the warming on our planet. And so it's really important to understand how the oceans circulate, because that affects how they take up that CO2. The oceans are super important for transporting heat, which is also important for our climate. So my background is as a physical oceanographer. So I study how the ocean moves, and I'm really interested in what that means for kind of our future climate.
Great. So too much CO2 in the air, and we need to do something about it. And my understanding is that this is a somewhat urgent issue. Is the urgency part of why you've turned your attention to this problem?
Certainly. I think for those who understand the climate system, we are concerned and feel it is urgent. As a physical oceanographer, I think I have turned my work to trying to understand the ocean's role in that. And I think one of the things that's really exciting about being an oceanographer is, in some ways, how little we know about the ocean, which leaves a big gap, for us to fill. And we know a whole lot about the atmosphere because we can send sensors up into the sky. It's not easy to do. It's not inexpensive, but it's a lot harder to work in the ocean. The ocean is huge. It's a huge reservoir of heat and carbon, and it's really hard to study. Observationally, the salt water corrodes all of our sensors.
Yes, of course.
Waves try to break our sensors, and so it's really hard to study the ocean.
Okay, great. So thank you. So now we've established that there's this problem, and now you have this really exciting kind of hypothesis or working theory that it may make sense to manipulate parts of the ocean, in particular seaweed, to kind of make a contribution to this CO2 excess. And so, can you take me through what is the theory there? And we must have knowledge that this is at least possible, and then we can talk later about the challenges. But what's the general idea?
Sure. Well, I think the big idea is that we have to reduce greenhouse gas emissions first and foremost. That is absolutely imperative if we want to forestall some of the worst effects of climate change. But it has also been appreciated in some recent modeling, global climate models, that in addition to reducing emissions, we also need to consider ways to actively remove carbon dioxide from the atmosphere. And so there have been a lot of people thinking about strategies, both terrestrial, so that's kind of what we think about planting trees and things,
Right? Love the
but
trees.
also the ocean is 70% of our Earth's surface. And it is this huge potential carbon sink. And so a lot of those strategies are considering ways to use the ocean. So seaweed cultivation is one of those, but there's many
So,
others.
so tell me, for what does seaweed do that's helpful? I mean, I know it's a plant, so should I just think of it as an underwater tree, or is it more complicated than that?
There are some similarities in that it is fixing inorganic carbon, so carbon dioxide is inorganic carbon, into organic carbon within its body mass. So it is an algae, it's a macroalgae. So it's using photosynthesis to fix carbon. And then, unlike a tree, which can often trees persist if they aren't burned in a fire, which
Right.
that's an issue,
Yes, it
they
is.
can persist for decades or hundreds of years, and that carbon is stored either within the body of the tree or in the soil beneath it. Seaweed are a bit different. There's lots of types of seaweed, so I don't, but for the most part, they are much shorter lived, and there's sort of high carbon throughput. So they're fixing the carbon in their structure, and then that carbon is broken down and used by other marine organisms. So that's not in
Ah,
itself a sink. It is kind of a flow through.
yes.
So you have to think about the final fate of that carbon if you want to consider seaweed as a carbon sink.
Good. So okay, I love this. So let's go there. Well, so the kelp, I guess it gets eaten by fish, microalgae, bacteria,
Mention all
maybe
kinds of.
us. And we can talk to that. But like, I have a bunch of salty little dried seaweed in little
Exactly.
packets that I like to eat. Because it is the throughput, and because it's not a big great tree just storing the carbon for future use. I guess before you start making changes, you need to have a theory about where it's going to all end up. Are we going to have overgrowth? Are we going to have algae blooms? I'm making this up. I don't really know what I'm talking about. But is it going to create changes to the kind of chemical and light and biotic composition of the ocean that might be worrisome?
No, these are all great questions, Russ. And I think, the theory is essentially that it's going to potentially capture carbon in much the same way that the ocean's biological pump does. So we have lots of microscopic algae called phytoplankton that are kind of the base of the food chain in the ocean. They grow near the surface, they get eaten by zooplankton, which are also small, and then the zooplankton get eaten by fish and bigger fish, and you can all see the cartoon in your head. And then eventually, when that larger organism dies, it carries that carbon with it as it sinks into the ocean. And it's carrying that into the deep ocean, which is not accessible to the atmosphere. So essentially, that is one of the ways that the ocean removes carbon from the atmosphere.
Okay.
And when you
So there
remove
is.
that,
I'm sorry to interrupt, but that means there is something like the tree equivalent. You were saying it's sitting there in the root system and in the main part of the tree, and kind of this sinking to the bottom in a long term storage is kind of the equivalent. Is that fair?
exactly, so the deep ocean sort of acts like the long-term storage, like the soil would.
Okay. Okay.
hmm Right. So I think then you need to understand, okay, well, then how much of that? if you're going to expand seaweed cultivation, say, beyond where it would naturally grow to try to turn up the dial on this biological pump, how much of it could make it to the deep ocean? And some people are actually doing some experiments, even in California here, testing that very thing. If we were to send, packets of cultivated seaweed to very deep places in the ocean, how long would it take for that seaweed to break down and that carbon to be released? How long would it take it to get back up to the atmosphere? And then, of course, we want to understand, what are we changing in
Right.
the bottom of the ocean now by putting this? Maybe it's not a foreign substance. Seaweed would naturally be down there, but maybe not in that quantity.
Okay, so this is so now my I'm excited and my head is exploding with questions. So, is the idea to grow seaweed near the coast, kind of near where the people are, and then bring it out? That's kind of the image that I think you just painted. Is I have a boat full or whatever of seaweed that I bring out to the ocean in the areas where it's very deep. I kind of plant it. Do I plant it at the top and hope that it falls, or do I push it down? Take me through how this might work.
Right. Well, I think the idea is somewhat like that. It's a lot easier to grow things near where you can get your boat, back to a port or
Right.
back to somewhere. So growing it close to shore is easier. But then you also want to be near somewhere really deep, so that you could get that biomass, that seaweed biomass deep. And so it's a compromise, right? And you can't grow seaweed everywhere. It
Right.
doesn't like to grow everywhere. In fact, often the near surface of the ocean doesn't have a lot of nutrients. And the reason is because all of those microalgae, those phytoplankton, have been using them. And
Ah,
so often, at least off of California, seaweed grows really well near the coast because of wind-driven upwelling, where deep water rises to the surface. That's why it's so cold when we go to the beach here in
yes.
California. Uh,
One of my
and
great
so it
regrets, but
grows really
that's a
well near the
different
shore. But
discussion.
if you were to take it offshore and try to grow it near the surface,
Okay, so that's what I wanted to ask you is so if we're starting to farm kelp and it's an exciting kelp. By the way, kelp is a form of seaweed, I presume, and I know that you've written about all seaweed, but you've also written about kelp. If we're growing that, then it's not that we can grow it everywhere. And in fact, as somebody who knows a little bit about biology, I'm going to guess that seaweed is growing pretty much everywhere where it can grow, because that's kind of what life forms do. Is that true? So is there a big reservoir of unkelped or unseaweeded area, or are we dealing with a finite resource and we're just going to have to manage and optimize it more?
no, I think you're right that for natural coastal habitats where seaweed could grow, these rocky reef areas where seaweed could grow, it has historically grown there.
Okay.
There are areas where people are trying to restore, kelp ecosystems where for example, here in California, we've had some very warm conditions over the past years, and in many places, kelp abundance isn't what it was. Now, there's some natural variability in that due to decadal ocean cycles, but by and large, we've seen a big decrease in bull kelp in some areas and macrocystis in other
Okay.
areas. Um, so those are two of our, main seaweed kelp species on
Right.
the West Coast.
So that's kind of good news in a weird way, because although we've lost the kelp, we know that in other situations it has grown there, and so maybe it just needs a little bit of a nudge. Are there any activities trying to bioengineer the kelp to kind of increase its
Mm.
range? I say that with some caution because we are not always very
Mhm.
successful at manipulating natural systems. But are people thinking about, oh, if we just kind of add some genes to this kelp or the seaweed, it'll be able to do things that are really useful?
Certainly, people have been thinking about the genetics of seaweed. In fact, I think the green revolution in agriculture spurred a whole lot of, obviously, as you're saying, some of these are unintended consequences. Not every bit of this is good, but we know a whole lot about the genetics of our terrestrial crops. We don't know a lot about seaweed, and we're just beginning to appreciate that we need to understand more.
Yeah.
I've been working with some other scientists at the University of Southern California who are beginning to bank different giant kelp uh, um, variants, and they have been looking at trying to see if some of those variants have thermal resilience, so can handle warmer temperatures. And we may want to potentially, if we're going to restore a kelp area, we might want to think about using a variant that has proven to be a little more resistant to warm
Yeah.
temperatures, since
Yeah.
we're likely to see some more warm
Yeah.
temperatures.
Great, great. And the other thing that I was thinking was you said that we'll have these special regions that can grow kelp, and then one model is you bring them out to the ocean and they sink in ways that we think might be beneficial and tree-like. What about the idea of bringing them onto the land? Are there models that where the seaweed product could be a useful part of the terrestrial ecosystem, either humans eating it, animals eating it as fertilizer, or things that I haven't even thought of? Are there any of those credible options?
Yeah, absolutely. In fact, we did some modeling, kind of a dynamic kelp growth model, kind of essentially planted, virtually planted seaweed of different types in every bit of the ocean. And then, not that we advocate that, but more
Right.
just as a first, how much could we grow if we tried to grow it? And then where would those hotspots be? And then we paired that with a techno-economic model to really understand how much would it cost to grow it in these spots that look good, that look biologically favorable, and then what's the value of the product? Either the value of a carbon credit that would be needed to offset the cost of growing it in this part of the ocean, or how much would you be able to get if you turned this biomass into a biofuel,
Uh,
or into a food, or into animal feed. And so there has been some interesting work that is looking at certain types of seaweed that, when fed to cows, can reduce the methanes in their burps for a
oh,
certain amount of time. Certainly, you can imagine that creating a biofuel that has a net zero carbon, because you growing it took the carbon out of the atmosphere, and when you burn it, you're adding it back. So that's the zero part. So there are a lot of other potential uses for seaweed besides sinking it to the bottom of the ocean. And in fact, a lot of people think those are a lot more realistic because we really don't understand some of the environmental implications of sinking large amounts of biomass deep in the ocean. We could really do some damage, to our benthic ecosystems by sinking a lot of biomass there. It takes up oxygen. We could
right.
kind of make some of our low oxygen zones worse, things like that. So.
This is the future of everything. I'm Russ Altman, and we'll have more with Kristen Davis next. Welcome back to the Future of Everything. I'm Russ Altman, and I'm speaking with Kristen Davis from Stanford University. In the last segment, we learned the basics of CO2, carbon dioxide, why we need to stop producing it and figure out ways to reduce it, why seaweed is a potential answer. In the next segment, Kristen will tell us that internal waves are an important component of the dynamics of oceans. It interacts with the CO2 problem, and it's also incredibly important to understand to see why oceans achieve the temperatures and interact with currents and the geography of the ocean. She'll also tell us that we have amazing new measurement technologies, including some based on fiber optics that can make amazing measurements of temperatures over long distances. So I wanted to ask you about the ocean itself, separate from the seaweed. I know you're an expert at the ocean, the physics and dynamics of the ocean, and this plays into the whole CO2 question because, as you mentioned, even in our first part of our conversation, there's intrinsic buffering capability, there's heat transfer that happens globally, and one of the concepts that's mentioned a lot in your papers are internal waves. And so I just wanted to ask you a simple question. What is an internal wave? Because it sounds cool, and why should I care about it as somebody interested in the ocean?
Sure. No, that's a fun question. Well, internal waves, as they sort of sound like, are waves that occur within the ocean. So, what does that mean? I think we're all fairly familiar with the concept of a wave in the ocean because we go to the beach and we see these waves on the surface of the ocean and they break on the beach, right? And so that is a wave that has often been created by wind blowing over the surface of the water, disturbing it, and then the the energy from that wind is propagating away with that wave. And that wave occurs because you have this really strong density difference between the air and the water. And when you disturb that surface, then gravity wants to restore that surface back. It overshoots, and you get this energy propagating away.
Okay.
Well, there are also differences in density of the ocean water within the ocean. Near the surface, we have warmer water that's been heated by the sun. Deep in the ocean, we have very cold water that has come from the poles, kind of been formed at the poles, flows down. So we have density differences in the ocean. And when we have things that disturb that density interface, then you can get internal waves. So I know everyone's probably been swimming in a lake where their feet were dangling in cold water.
Yes.
And up at the surface. Maybe you floated to stay on the warm water.
Absolutely. The top 8 inches.
That's right. So when you were kicking your feet in that cold water below, you were probably generating internal waves heading out from where your location. So just like if you plunk a rock in a lake, that surface, those rings propagate away, you were doing the same thing with your feet and the bottom. So we don't see internal waves very often because they're not at the surface of the ocean, but they are extremely important. In fact, they are the answer to probably one of the biggest mysteries in physical oceanography. When oceanographers first started to study the distribution of heat and salt in the oceans, and they realized that there must be a certain amount of mixing to result in the observed structure. But every time they would go out on a boat to measure it, they always found mixing levels to be orders of magnitude less than was suggested by the structure of the oceans. And so for a long time, there was this mystery of where is all this mixing happening that is resulting in the structure of the oceans. And it turns out that the answer was internal waves, that these waves are generated often on topography that is kind of scattered throughout the ocean. There's actually underwater mountains within the ocean.
Right.
There's a lot of steep topography near land.
Yeah, the trenches. We're all excited about the trenches.
Right, exactly. So there's a lot of internal waves that are generated in those regions, and they drive a lot of the mixing. But it's just kind of episodic in time and spread out in space. So it's actually kind of difficult to measure.
So let me ask you a super basic question, which is we also hear about currents in the ocean. What is the relationship between currents and internal waves? Because they sound a little bit similar. Like you don't see the currents, you might feel them under your feet, blah, blah, blah. So tell me about currents and internal waves, the differences or similarities.
Right. So often when we're talking about currents, we're talking about the movement of water that persists for a longer time and is sort of in a particular direction.
Right. The famous
so we have some
streams
large-scale currents, right? Like the Gulf Stream or California current. And so those we tend to think of as currents, but currents can make internal waves. In fact, many internal waves are made by tidally driven currents. So the tide sort of drives currents back and forth. And when you drag that water that's stratified, had changes in density is what I mean by stratified, over topography, you essentially can generate a disturbance in that density interface. And just like you're kicking feet in the lake, and then that energy propagates away as an internal wave.
Great. So now we have a pretty good understanding of internal waves. Thank you. And just one quick question, which would be, does the dynamics of these internal waves inform the way you're thinking about the Seaweed project that we talked about earlier?
In fact, it does. Because internal waves are so important for mixing energy mixing nutrients actually back up to the surface, where they can be used for photosynthesis. We are also exploring, would it be good to place seaweed farms in places that have internal waves, because then you can access more nutrients to grow the seaweed while also staying near the surface so that you can get sunlight to grow.
you might benefit also. You were talking about this was a solution to this big mystery about mixing, and we would get a certain amount of mixing of the seaweed, presumably in a similar way.
Right, actually, seaweed, it's very important to seaweed to have flow across the seaweed. It's helps the seaweed to actually take up nutrients from the water column around it to be in a place with some flow. So
Great. And so this is a major area that we're looking at in order to understand kind of the biophysics of how the ocean interacts with itself and with the land. And it was a missing concept for many years. How do you measure these things? I mean, in the last few minutes, you're an engineer. You're going to these
Mhm.
amazing places, studying the ocean. You already said that the salt water is a pain in the neck. It rusts your equipment and corrodes it. What are the new measurement technologies that you or others are working on that's allowing you to access these kinds of phenomena in a better than previously?
Sure. Well, one of the really exciting ways that we are have recently been measuring internal waves and learning a lot about them is through a fiber optic instrument, essentially a fiber optic cable, that we can measure temperature along the cable. So essentially, we send a pulse of laser light down a fiber optic cable, and the backscattered light is has some signature in the spectrum of the temperature of the location where it was scattered back. And so if we understand the speed of light, which we do, and we know the length of our cable, we can essentially turn a fiber optic cable into a continuous temperature sensor. And so we've used one of these cables, a 5 kilometer long cable,
Wow.
in one of the places in the world where there are some of the biggest internal waves. So I know we talked before, just earlier, about surface waves at the beach. A big day for me, I'm a very novice surfer, at the beach would be a
I would be
wave anything.
disappointed if you were not a surfer, by the way, but that's a separate discussion.
Frankly, anything over about a meter, I'm terrified. But if you in the South China Sea, which is where we've been studying these internal waves can be over 100 meters in amplitude. So really, really big. And the reason is because the density differences between the warm water and the colder water are much smaller than, say, air and water. So
Yeah.
these waves can be really big, but they drive massive flows. And in fact, the place we're studying it is on a coral reef where they deliver cold water up to the reef. So we've been using one of these fiber optic cables there to understand the breaking and shoaling and kind of
Yes.
the
What
final,
is the
the last
resolution
stages.
along your 5 kilometer? Are you getting a measurement, so to speak, every 10 meters or every 100 meters? What is the resolution of your temperature measurements?
In that deployment, we were getting a resolution every meter,
Oh
right?
my
So it'd be like
goodness.
having 5,000 temperature sensors all laid out, one after the next, coordinated in their measurement. That would be a lot of work. Putting in this fiber optic cable was not trivial, but
I
it
was going to say the
provided
China Sea might not be the most like geopolitically stable best place to put down a fiber optic cable, but it sounds like you figured out how to do it.
yeah, it definitely was a little challenging, but we were actually working with from a Taiwanese national park called Dongsha. It was a really exciting place to work.
And so is the dream to get these cables, or either to take these cables and make multiple measurements around the world, or to have a standing set of sensors so you can monitor? What's your dream for this very powerful technology?
Yeah, I mean, I think to use the same instrument in other locations to see if some of the things that we've discovered about these internal waves as they're shoaling, you know, this area is, as I've talked about, is an extreme example.
Yeah.
These are huge waves. We want to see if some of these same things apply in other places. Because what we'd really like to establish is a general understanding, a fundamental understanding of the internal wave physics, the
Yes.
dynamics that drive this mixing. And so I think this instrument is really promising. It provides us a totally new perspective.
It's very easy for me to imagine that given the success of those measurements, the urge you must have to take that cable or clone it and just bring it to lots of places to kind of do a survey of what's going on. And you could see, you knew that it sounds like you were very clever. You went to the spot where you were expecting big measurement, differences. And now you're going to get, I'm just extrapolating and guessing. Now you say, okay, let's get a little greedier and try to measure the smaller waves. Let's do it on a systematic basis all over and kind of get a map of these, of the wave space, so to speak.
Exactly.
Thanks to Kristen Davis, that was the future of seaweed. Thanks for tuning into this episode. We have more than 250 episodes in our back catalog, so you have access to a wide variety of interesting conversations with experts on a variety of fields, all relevant to the future. If you're enjoying the show, please remember to tell your friends, family, and colleagues about it. Word of mouth is a great way to spread news of the podcast. We would like to go viral. You can connect with me on many social media platforms, including LinkedIn, Blue Sky, Mastodon, and Threads. I'm at RB Altman or at Russ B. Altman on these, and I post about every episode as it comes out. You can also follow Stanford Engineering at Stanford ENG.